Welcome back from that short ad break. Let's continue our investigation of energy and the photon. So, earlier we looked at how there are the different frequencies of electromagnetic radiation in the spectrum also have different wavelengths, and we used a little bit of our understanding to start to understand this idea of the energy associated with electromagnetic radiation. Now, as part of that, we need to show, or we want to determine whether there is some mathematical relationship between the frequencies of electromagnetic radiation and this energy that it is transferring. So, we need to have a look a little bit deeper and try and see if there is some kind of relationship between the frequency of electromagnetic radiation and the energy that is transferred by it. So to do that, we need to have a quick reminder of what we already know about the spectrum of electromagnetic radiation. From our work on the spectrum of electromagnetic radiation, we already know that higher frequencies of electromagnetic radiation have smaller wavelengths. Do you remember this from last time, where we looked at electromagnetic radiation with different frequencies and then saw that as the frequency got larger, the wavelength tended to get much smaller? Well, is there more to this? Let's have a look. This is a GIF that we've already had a look at, and in it you can see two electromagnetic waves, or two waves. Number one at the top and number two at the bottom. In number one, we can clearly see that the frequency of the wave is quite a bit higher than the frequency of the lower wave, wave number two. If we watch the numbers, we can see that in the time it takes wave 1 to complete 8 full wavelengths, our wave 2 has only just completed 2.5 wavelengths. So certainly the wavelength of number 2 is quite a bit larger than number 1, and that is because the frequency of wave 1 is higher. Now, we've already seen this relationship between frequency and wavelength, haven't we? But now we want to try and determine if there's some relationship between either of them and the energy of the electromagnetic radiation. So let's lean on past physicists and see what they have to say. So we are still posing the question, what is the relationship between frequency and energy? To begin, we should remind ourselves of what we already know. We are a lot more careful and wary of electromagnetic radiation that has a higher frequency. Think of our X-rays and our gamma rays. They're the ones that you don't want to be exposed to. But remember that they also have smaller wavelengths due to their higher frequencies. The question we can ask ourselves is simply why, and how does this relate to energy? The answer, quite simply, is energy is proportional to the frequency of electromagnetic radiation. This means that as the frequency increases, the energy of electromagnetic radiation increases as well. Had you already realized this? That the more dangerous electromagnetic radiation had to have a higher frequency? Well, other great physicists noticed it as well. And they went to try and find if there was a way to equate the energy to the frequency of the electromagnetic radiation delivering that energy. So let's have a look at what they found. So we've already said that energy is proportional to the frequency of electromagnetic radiation. But importantly, it is not equal. We cannot say that the energy transferred is equal to the frequency. So, how are we going to make them equal? A common problem in physics is trying to find how certain quantities or variables can be said to be equal. To get our answer, we're going to ask Max Planck. Have you heard of Max Planck before? He's a famous physicist from 1899 who did some interesting research on electromagnetic radiation. Let's see what he had to say. Max Planck was able to show in 1899 that the energy and the frequency of electromagnetic radiation was proportional. But he was not satisfied with this discovery. He wanted to be able to calculate the energy for any particular electromagnetic radiation at a certain frequency or wavelength. So what did he do? Well, he did a series of experiments, and through experimentation, he found how to equate the energy and the frequency, i.e., how to get an equation that would give us how frequency and energy are related. To do this, he used a constant. Recall we mentioned the constant earlier. A constant is simply a variable in maths or physics that always has the same value no matter what. This constant is named after him and his research and its impacts on history, and it is called Planck's constant. It's a very small number, and it is given the symbol h. Its magnitude is only 6.63 times 10 to the minus 34 joule seconds as a unit. But, valuably, it gives rise to a new formula for us to use. In this formula, we are able to equate the energy of an electromagnetic wave to its frequency by multiplying the frequency by Planck's constant. This gives us our energy reading in hertz. So, had you heard of Max Planck before we mentioned him in today's lesson? Did you know that he was able to develop such an important formula, one that lets us relate energy to frequency? What does this formula, though, allow us to say about that relationship we started with? What does it allow us to understand about the relationship between energy and frequency? Let's have a look. So from this equation, E is equal to h times F, we can see that the energy is proportional to the frequency. Don't worry about this symbol here. It just means that the two variables are proportional, i.e., as the energy increases, the frequency had to increase at the same time. So we say, for the relationship between frequency and energy, that as the frequency increases, the energy of the electromagnetic radiation also increases. Now, you can see this in I've used a normal algebraic sum to help us understand this. I've replaced our constant h with a constant that's just a numerical value, number 6. If we had a function that said y is equal to 6 times x, we would all be quite comfortable with the idea that as x increases, y's value will also increase. But remember, in our cases, h is always a constant. So now we've seen that there is definitely a mathematical relationship between energy and frequency. But what about the wavelength of the electromagnetic waves we've been talking about as well? Is there a relationship there? Let's have a look. So from our formula, E is equal to hf, we are actually able to replace the value of frequency with c over lambda from our wave equation for electromagnetic waves. And this gives us a new expression for the energy of an electromagnetic wave, where E is equal to Planck's constant h multiplied by the speed of light, all divided by the wavelength of the electromagnetic radiation in meters. And again, we can see that now there is a proportionality. But instead, our proportionality is an inverse one, i.e., as the wavelength of electromagnetic radiation increases, the energy of it decreases. I've used another simple algebraic sum to show you again. if we had a function where y was equal to 6 over x, remember 6 is our placeholder for our constant, just like h is our placeholder for Planck's constant, we can clearly see that as x increases, y's value would decrease. All right, so now we've clearly shown that there is a relationship between energy of electromagnetic radiation and the frequency. We've seen that as the frequency increases, so does the amount of energy transferred. And as the wavelength increases, the amount of energy transferred decreases. But what about that idea of penetration we talked about earlier, when something goes into a material? Let's have a look. When examining the idea of penetration, now that we understand the energy of electromagnetic radiation, we're better equipped to understand why some electromagnetic radiation is able to penetrate materials and why some isn't. And the answer lies in the amount of energy. The greater the energy of the electromagnetic radiation, the greater its ability to penetrate into materials. And when they when high energy electromagnetic radiation penetrates a material, it is able to transfer energy to it. So now we've seen that penetration is also linked to the amount of energy. And this maybe starts to help us understand why we take precautions when working with certain types of electromagnetic radiation. Can you think of some precautions that you take on the daily? Let's have a discussion about it. So when should we be careful? Obviously, we should be careful when electromagnetic radiation outputs a high amount of energy, i.e., when it has a high frequency and a low wavelength. But maybe you also recall that many things like cell phones use electromagnetic radiation to send signals around the world or around the country. So when do we have to be careful? Why do we put on sunscreen when we go outside, but you don't worry about wearing sunscreen when using your cell phone? As we go further, hopefully we'll be able to answer these questions.